When it comes to vector multiplication, there are two methods to take into account. The first one, which was explained in the previous video and can be found in the upper right corner of the screen, is called the dot product. The second method, on the other hand, is the cross product and will be the main topic of discussion in this video. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. In many applications of vectors in mathematics, physics, and engineering, there is a need to find a vector that is orthogonal to two given vectors. Let's begin our discussion from this point. Imagine we have two non-zero vectors, u and v, and we need to find another non-zero vector, t, that is perpendicular to both u and v. In other words, we want to find a vector t such that u dot t equals 0 and v dot t equals 0. Therefore, u, v, and t must satisfy the equations below. If we multiply the top equation by z sub 2 and the bottom equation by z sub 1 and subtract, we can eliminate the variable z sub 3, which gives. We can rearrange this equation. This equation in two variables has many solutions, for which a particularly easy one to see is given as follows. After substituting the given values into one of the initial equations, we can solve for z sub 3. Then we can determine the coordinates of vector t, which is perpendicular to both u and v. The vector t is called the cross product of u and v and is denoted by u cross v. The formula to find the cross product of two vectors is straightforward, and it presents to cross product in the useful component form. The formula, however, is complicated and difficult to remember. Thankfully, there is another option available since the structure of the right-hand side of the formula matches that of the formula used to calculate the determinant of a 3 by 3 matrix. The formula for the cross product of two vectors can be expressed as a determinant of order 3 with the standard basis vectors as the elements of the first row. If you are not familiar with evaluating determinants, I suggest watching the video located in the upper right corner of the screen before proceeding. The cross product results in a vector, so it is sometimes called the vector product. We now turn to the main concept in this video, and we introduce the cross product, which is defined as a determinant as follows. If you have two vectors in 3D space, vector u and vector v, the resulting cross product u cross v is the vector perpendicular to both vector u and vector v defined by for vector u and vector v, find each of the following. To solve item A, we begin by writing down a determinant, which is an array of numbers. In the first row, we write the three unit vectors I, j, and k. In the second row, we write the three components of vector u, and in the third row, we write the three components of vector v. The 2 by 2 determinant and is evaluated by finding the product of the elements on the leading diagonal, top left to bottom right, and subtracting the product of the elements on the other diagonal. To solve part B, we will follow the same steps, but replace the second row with the third row. When comparing the vectors u cross v and v cross u, it is evident that they have equal length but opposite directions. This is a fundamental property of the cross product, and it highlights the fact that the cross product is not commutative. We summarize some of the basic algebraic properties of the cross product as follows. To prove these properties, one can express the vectors in terms of their components and apply the definition of a cross product. The cross product between vector u and vector v points in a direction that is perpendicular to the plane formed by the two vectors. To determine this direction, you can use the right-hand rule. When you curl your right-hand fingers in the direction of a rotation from vector u to vector v with an angle less than 180 degrees, your thumb will point in the direction of u cross v. Once we determine the direction of vector u cross v, we still need to determine its length to fully describe it geometrically. The following theorem outlines some significant geometric properties of the cross product. If theta is the angle between vector u and vector v, then the magnitude of the cross product of the two vectors u and v can be computed by multiplying the magnitude of vector u with the magnitude of vector v and the sine of the angle between them, represented by theta. To prove this property, we use the definitions of the cross product, the dot product, and the length of a vector. The second property states that the cross product between two vectors is zero if and only if vector u and vector v are parallel vectors. This property is an immediate consequence of the first property because two non-zero vectors u and v are parallel if and only if theta is 0 or theta is 180 degrees. In either case, sine of theta is 0. This third property states that the length of the cross product u cross v is equal to the area of the parallelogram determined by vector u and vector v. To prove this property, we locate vectors u and v such that they form adjacent sides of a parallelogram. To find the area of a parallelogram, you can use vector u as the base, and the height can be calculated by multiplying the length of vector v with the sine of theta. The magnitude of the cross product will give you the area of the parallelogram, which is equal to the product of the base and the height. Let's see how it works. We can calculate the cross product with a determinant. To find the angle theta, we use the inverse sine function. To find the area of a parallelogram, we calculate the length of the cross product of a vector u and vector v, which was already calculated in part B. The cross product u cross v is orthogonal to both vectors u and v. To find a unit vector with the same direction of u cross v, we divide the vector by its magnitude, so the unit vector is given as follows. We now learn how to use the vector product to calculate the volume of a parallelepiped. Let's consider the parallelepiped spanned by the vectors u, v, and w. The volume of the parallelepiped is the area of the base times the height. We know that the area of the parallelogram base is the length of the cross product, and that the direction of the vector u cross v is perpendicular to the base. The height of the parallelepiped is the component of the vector w in the direction normal to the base, that is, in the direction of u cross v. Therefore, the height can be calculated by multiplying the length of vector w with the cosine of the angle theta. Theta is the angle between vector w and the cross product of vector u and vector v. We use the absolute value of cosine theta to account for cases where theta may be greater than 90 degrees, resulting in a negative value for cosine theta. The volume of the parallelepiped is, but the length of u cross v times the length of w times cosine of theta is equal to the dot product of u cross v and the vector w. Therefore, the volume of a parallelepiped is the absolute value of the dot product of vector w and the cross product of vectors u and v. The quantity inside the bars is called the triple scalar product. It is not necessary to compute the dot product and cross product to evaluate a scalar triple product. The value can be obtained directly using determinants as follows. The formula for the scalar triple product of vectors w, u, and v is given by the determinant of the components of the three vectors. Let u, v, and w be non-zero vectors in R3. Then the number expressed by the dot product of w and u cross v is called the triple scalar product. We can write the scalar triple product as a determinant. The volume V of a parallelepiped with vectors u, v, and w as adjacent edges is. Let's see how it works. First, we compute the triple scalar product and then find its absolute value.